Good afternoon, everybody. Thanks for taking your time to come see me talk a little bit about our purpose-built database strategy. This is our DAT301 session. We're matching the database to the workload, and I'm going to talk about exactly that subject. So hopefully that's what you're here to see. If not, we just had lunch. It's a nice warm room, so feel free to kick back, close your eyes, and take a little nap. I think I'm going to be a little more interesting. All right, so what we're going to talk about this session is, generally speaking, we're talking about workload classifications for databases, right? What workload makes the most sense for what database, and so we're going to get into the dimensions of a workload and the types of workloads that typically make up modern applications that we work with today. We'll talk a little bit about some of the traditional approaches to scaling the relational database, because the relational database has been the back-end platform for every application that we've pretty much built over the last 30, 40 years or so, until the advent of NoSQL technology. And then we'll talk about how NoSQL databases actually compare when it comes to scale, design patterns, and data modeling, whatnot. We'll get into some of the flavors of NoSQL on AWS. As you're probably aware, we have a purpose-built database strategy with lots of options, and we'll talk about what flavors of NoSQL we have and when it makes sense to use a graph database like a Neptune versus DynamoDB, and when it makes sense to use a relational database for your application, because there's plenty of workloads that still require that. And that's generally what we'll do to fill out the session, is what database to use when and for what workload. So I deal with a lot of development teams. I do a lot of migrations of relational databases to NoSQL. As a matter of fact, for the last year and a half, actually up until about 6 months ago, for the year and a half prior to that, my primary goal in life was to migrate the Amazon retail organization. Many of you probably read the effort we've had to move everything off of Oracle backend and into a NoSQL platform. That means DynamoDB. So I've worked with, we have about 350 or so what we call Tier 1 services. These are services that are revenue generators. When they're down, we're losing money, and that was one of the biggest reasons why we decided to move off of Oracle, because we were going down way too often. So we moved this up to a more scalable platform, because the data load, and this is really what I've seen over the last year or two, is that the common app is becoming a big data app. Right, so we're seeing a lot more types of applications that previously maybe would have been okay with the relational backend. They're now hitting that scale barrier, and we'll talk a little bit about that. But when I go to teams and I talk to them, I ask them these questions, right? What did you use? Why did you choose this database, for your workload? And generally, I get these answers. It's well, because we heard it's a really the new exciting technology, right? We've got to use NoSQL. I want to use MongoDB because MongoDB is awesome, right? And it is, but it's not necessarily awesome for everything, right? NoSQL is really a great technology, maybe because we have a site license for this technology. We hear that a lot. We have a site license for Oracle or MS SQL Server or something like that. It makes more sense for them to use that. And then it's because the third option that we get, third answer I get, is it's because we know how to use it. Okay, which I suppose that's a good answer as well, but the reality is what you really want is you want the database that's purpose-built, to support what your application is designed to do. If you want to be cost efficient, you want to be performant, then we need a back end that's going to be responsive to the needs of your workload. So what does that really mean when we talk about workloads? It really breaks down into a couple of buckets, right? Really two buckets. We have an operational application and we have an analytical application, right? The operations application is what we traditionally have referred to as an OLTP, or online transaction processing app. An OLTP app represents a common business process. It's one of the most common applications that we build today. Common business processes are regular and repeatable. The same thing happens every time that the data is processed. So that's what would be an OLTP or an operations application. The other types of workloads that we have are OLAP workloads. These are analytics workloads. So think BI, business intelligence or reporting types of applications. And typically these applications have more what we'd call ad hoc access patterns, right? We don't really know what questions the users are going to be asking when they come into the application. So there's a totally different set of requirements to support a regular and repeatable business process versus support the ad hoc queries. And then the other type of application workload that we typically see is a decision support system. These are scaled out data lakes, data warehouses. We're running long-running queries and workloads against semi-structured data because we're trying to answer questions for the business. So if you think about how these analytics applications break down, we have our OLAP or workload, which is really going to need a more responsive framework. These are types of real-time queries I'm expecting answers for in line with maybe a user's request, versus a data warehouse or a decision support system or a data lake, which is maybe I'm going to run queries where latency isn't really the biggest deal. What I really want is the answer, and I might be running that query across some distributed document store, and it's okay if it takes a couple seconds for the answer to come back. So think of your dimensions of your workload along these lines as, I need, maybe one dimension might be the need to support ad hoc queries, right? Or the need to support efficiency in the query, right? So there's a couple of dimensions that we're talking about. The nature of the access pattern itself, and the reality of the amount of response time that I'm expecting from the system. Those are two very important dimensions when I get into looking at what my workload might require. They're not the only dimensions. We'll talk about some other ones. But the next thing we want to look at is sizing the workload. Right? It's, depending on the nature of the application that I'm working with, I have different requirements for my back end. Obviously, if I have a problem with limited scope, it's easy to solve. If maybe I have a point of presence or a point of sale system that would be deployed inside of a convenience store, I can have a single computer that runs behind the cash register that manages my inventory, my billing, my invoicing, all of the things that I need in my store, and that's a very small problem, and I don't necessarily need a lot of infrastructure, but unbounded problems are much harder to solve. Maybe if I wanted to build a system that was capable of doing root cause analysis for market events across global markets, looking at millions and millions of trading events, and we've actually built an application to do this for one of our customers. That's not an easy problem, and it's not a problem that's going to be solved on a single desktop computer sitting behind a cash register. Right? Obviously, I need a bigger system, a lot more infrastructure, and a totally different database to be able to run that application. So that's an extreme example, but there's various degrees of data pressure, you could say, in a given system. Right? So the scale of the system is another dimension that we need to be aware of when we're working with and trying to choose a database. So to that end, let's look a little bit about what it takes to size the database. And so typically when we've sized a relational database, it's about adding incremental chunks of capacity, and that's great, but that leaves us with a situation that oftentimes looks very much like this. So we have maybe some amount of capacity that we're not utilizing, and that's really wasted dollars. And at some point, we're going to cross the line and say we're perfectly provisioned, and then all of a sudden we're having a bad user experience because we're under provisioned and we need to add more capacity. But it's very, very difficult to find that balance between the amount of capacity that I have available and the amount of demand for my application or service that is present. So this is kind of the problem or the conundrum that we face as we start to provision capacity, and it's that step function that really makes it difficult. Right? If we add capacity in chunks, and the way we've actually done that with the relational database is to do exactly that. You start off with a small box, it can do a certain amount of work. As that workload increases and the demand for that particular application service increases, we're going to go and get a bigger box, and eventually we're going to get a bigger box, and eventually we're going to run out of big boxes. And then we're in trouble, right? What do? And then we go into a situation where we actually have to start sharding the relational databases. I ran into this situation at a previous company about 10 years ago. We were doing event management in ITSM, IT Systems Management Software. And the event load of enterprise IT infrastructure, especially for a large enterprise, is extremely big. I mean, we're talking about, I was working with a customer who had over 1 million network devices on the West Coast alone, and had a policy of capturing every event that came off of all of that infrastructure. We were literally partitioning our MySQL database every day to support this, and they had a 5-year retention policy. So we're looking at that and going, okay, with 1,900 instances of MySQL, I think we're going to have a problem managing that system. So we thought maybe we need a better solution. And that's when we started looking at NoSQL. I started digging in to the differences between the relational database and the NoSQL platform. So NoSQL databases leverage a denormalized data model that is sharded or distributed across multiple storage nodes or processing servers to provide a nearly unbounded throughput and storage capacity. And we'll talk a little bit about how that works. But the idea here is to get away from the relational data model, which requires us to kind of co-locate all of the data in the same processing space, which is the primary limit or limiter of scale with a relational database. So the way NoSQL databases work is we're going to distribute these items across an arbitrary key space using an attribute in all NoSQL databases must have called a partition key. And it looks like some of my graphics are missing on these charts. I don't know why. Those little items should have a couple of attributes in there. One of them would be a partition key that we're calling ID. So we're going to hash the ID value. We're going to distribute these items out across this arbitrary key space. And as I need to scale the system now, all I need to do is chop that key space up and spread those documents out across multiple physical storage nodes. This is how all NoSQL databases work. We need to get those documents spread out, those items spread out across some physical key space that can be chopped up and spread out across multiple physical devices in order to provide more compute, more storage capacity, for the database. Now, when I query the database, what I'm going to do is provide that partition key value and tell the system where to go to get that data. In DynamoDB, we call it a partition key. In MongoDB, they call it a shard key. In Cassandra, they call it a partition key. But every NoSQL database must have this mechanism, or we won't be able to spread those documents out across multiple physical nodes, and we won't know where to go when the query comes in. You give me some shard key value, I know I need to go to this specific device. And that's what makes NoSQL databases fast and consistent at any scale. So when we get into NoSQL, and this is just this is something that has been such a theoretical concept for relational databases because there's just been no choice. Relational databases need to perform in a very specific manner. NoSQL databases make some choices, and we'll talk a little bit about this. But this is the CAP theorem. It's the iron triangle of data, so to speak. If you're familiar with project management, you have this iron triangle of 3 dimensions. It's either you're going to get it fast, you're going to get it cheap, or you're going to get it good. Pick 2. You can't get all 3. Well, data has its own iron triangle. It's called CAP. Let's talk a little bit about those particular dimensions. The consistency is the first one we'll talk about. And consistency is about the ability of all clients always having the same view of the data in the system. No client can log into the system and get a different view of data than another client at any given time. So consistent view of data. When data is written and read immediately after it's written by another client, then they're going to see the same data that was written by that client. Availability is the ability of the system for all clients to always be able to read and write. It's important to understand both dimensions must be satisfied in order to be an available system. If I can only read the data but I can't write, then it's not a fully available system. So relational databases have chosen to always maintain this consistent and available view. And now the third dimension is what we call partition tolerance. And this is about what happens when the connection between the devices that constitute the database, the storage nodes that constitute the database, start to fail. Right, the network connectivity, and I insert partitions between these storage nodes. What's going to happen? And so this is really the crux of what NoSQL is all about. We make some decisions here. So the first, again, we get to pick 2 of these dimensions, and if you look at the relational databases, the 2 that they picked are consistency and availability. And they do this by locating all of the data on the same storage space, on the same processing space, right? So we don't have to worry about partition tolerance because I cannot partition the data store. All the data in a relational database instance lives in the same storage device in the same processing space. There's no shared or sharded processing of that data. Now, NoSQL databases have to make a choice because we're going to break that consistency and availability when we go to a distributed database model, because now we're introducing this concept of partition tolerance. And how does the database react when that partition is introduced into the environment? So the first choice we have is to say, well, we're going to be consistent and partition tolerant, and we're going to punt on availability. What does that mean? That means I'm going to have some sort of a primary node that all writes are going to go into. If that primary node were to fail, or there was a network partition inserted between that primary node and the other storage nodes, there would be some sort of election process to determine whether or not that primary needs to step down and we need to promote a new primary. During that period of step down and failover, then some of those clients on the network are not going to be able to write data into the system until that new primary becomes available. What this means now is that's a consistent system, because nobody can write data while we don't know who the master is, and all data has to be written through the master. So if I read from the master, I'm going to be able to get a consistent read. Other NoSQL databases make a different choice. They make the availability and partition tolerant choice, or the AP choice. This is what was commonly referred to as master-master configuration. I can write anywhere. It doesn't matter what node fails. I'm just going to write data into the system at any node. That data is going to replicate around the ring or the cluster, so to speak. And as we detect conflicts, where we've had items that are updated in multiple places, there's some conflict resolution logic or some callback that's going to be executed to be able to resolve those conflicts. Mostly it's time-based. Right, I'd have some sort of NTP synchronization of my hosts. If a host fails, or a host receives a replication from another place and there's a conflict, because I've updated my data, we're going to look at the timestamp and the last update wins. There's also the ability in some systems to provide more complex logic. DynamoDB is a database that provides consistent and partition-tolerant functionality out of the box. Within the region, we are a CP system, but with the introduction of global tables, what's interesting is that we become the only globally distributed managed NoSQL service that provides master-master functionality. So we are actually both a CP and an AP system. We run CP within the region and we're AP across regions because of the replication from multiple regions. Now, conflict resolution with global tables is strictly time-based. So we maintain clock synchronization across regions, and as writes come into the table, if there's a collision, because I updated in multiple regions, then the latest update is going to win. So that's how that works with DynamoDB. Other databases make different choices, as you can see, a variety of NoSQL technologies, but all NoSQL technologies have to make that decision. Am I going to be a CP system, or am I going to be an AP system? Because we're breaking that CA branch, which the relational databases use. One of the most important things when you're looking at new technologies like NoSQL, really any new technology, and this chart is about learning how to use new technology. As we naturally start to use new technologies, we're going to take the design patterns and best practices that we've learned in the past, and we're going to try and apply those to this new technology. And oftentimes, that's actually the worst decision you can make, because most of the time, new technology doesn't work the same way as the old technology, right? I mean, when we used to bust concrete with the sledgehammer, and I'd swing it over my head, right? And then the jackhammer comes along. I don't swing the jackhammer over my head. I'm much more efficient using the jackhammer with a different approach. It's the same thing with technology. This what this chart is about. If you look at the bottom of the chart, it's the adoption curve, right? So as we, in the early part of the market, for a given technology, there's some sort of challenge, technical challenge, a technology trigger is forcing innovation. We invent new things to solve these problems. Some people have good experiences with this new technology, and then everybody starts to run to the new technology, say, hey, that's going to solve my problems. The problem is they don't learn how to use the new technology first, and they try and do the same thing. And this is that they did with the old technology. This is the biggest problem I run into at teams using NoSQL technology, is they're actually using relational data modeling. And they're going into a NoSQL database, they're implementing a parent-child relationship, they're implementing many relationships, they're implementing multiple tables with lookup tables and the whole 9 yards, and then they're wondering, why isn't it working? Why is it so expensive? Why is it so slow? And it's because you're managing the joins at the application layer instead of denormalizing the data model properly. So if you want to have a better experience with any new technology, you want to avoid that trough of disillusionment, so to speak, you're going to want to learn how to use that new technology first. And if you look at relational technology, we're all the way out on the right-hand side of that graph. If you don't know what an inner join is today, then I don't know where you've been for the last 3 decades. Maybe you need to go back to school. But it's not the same with NoSQL technology, right? We just don't know it. Most developers have little experience with it, and even, again, they come in and they start to assume that it works the same way. So as that skill set starts to commoditize across the market, you're going to start to see that slope of enlightenment is going to become more and more common, that kind of productivity increase as the skill set starts to distribute. I think today that NoSQL technology is firmly planted in that early adopter, maybe even in the technology gap. Right now, we still haven't cleared that point. There's no, the skill set has not diffused, right? When we start to see the majority of developers today understanding NoSQL technology, then we're going to be in that early majority, right? I mean, probably the clearest indicator of this is I don't interview a developer today and ask them, what is an inner join? Nobody asked that question, right? But when I did 25, 30 years ago when we interviewed developers, yes, we had to ask that question because developers didn't understand how to normalize their data as much as they do today. Today, it's like the back of our hand. The same thing will happen with NoSQL technology over the next 5 to 10 years. Denormalized data modeling is going to become commonplace, and people are going to understand what that really means. And if you're interested in that, I gave a great session last night, the DAT301 session. It's up on YouTube already. Talks a lot about design patterns and best practices for NoSQL. All right, AWS has an enormous array of technology for you to solve your problems, and we've really analyzed our approach here to try and decide what's the best way to go after this. Certainly we can stand up an API in front of maybe a DynamoDB, and we can provide various forms of these types of interfaces, a graph function, a time series function, whatnot, in front of a generic NoSQL store. But that flexibility comes at a cost, and that cost is typically dollars in efficiency. So what we decided to do instead, when you look at modern application frameworks, they're not all about a single monolithic application, right? They're about services that comprise an application, and those services might have different dimensions to the workload that they're supporting, which means we might want different back ends, right? And oftentimes these services don't even work with data that's even related or connected, and it might be better served to spread that data out across multiple back ends. So this is kind of the approach we're taking by providing these specialized solutions. If you look at NoSQL offerings today, we announced a few really cool new offerings. I'm not actually going to talk too much about those today because they're still new, but the use cases for those technologies are evident, right? If you look at NoSQL solutions, DynamoDB, Neptune, TimeStream, QLDB, it's an amazing array of solutions for you. The relational database solutions, RDS and Aurora, and in getting into analytics, Redshift, Athena, EMR, such a variety of services for you to be able to use that basically we can handle any workload and any dimension of any workload with one of the database backends that we offer. Getting into the individual services, I'm not going to spend a lot of time talking about RDS, again, because it's a relational database and it's so well understood. Probably the best points to talk to with relational at this point is because it is an option in the array of database services that are out there, and it's not the only service available to us anymore, is really to understand when do I want to use a relational database. And again, we talked about the OLAP style workload, and that is the sweet spot for relational. Don't try and solve ad hoc query workflows with a NoSQL database because it's going to be a difficult chore. NoSQL databases like to tune the data model to the access pattern, which kind of means I need to understand the access pattern before I model the data. Relational databases reshape the data on the way out, and they give you an ad hoc query engine on top of that so I can write all kinds of queries to reshape the data to support any type of access pattern I want. So that's a fundamental decision-making criteria for whether I should use relational or not. Is it an application that requires ad hoc queries, or the access patterns are not well understood? You're probably going to be better off with the relational database because those access patterns are more flexible. Once you structure your data and tightly couple to the access pattern, it's difficult to unwind that. And so NoSQL databases shine in that OLTP use case, whereas relational databases shine in that ad hoc use case. If you look at Amazon DynamoDB, it is a wide column key value store. It supports both document and attributes and first class attributes. It's a highly scalable system. It's fully managed, and that's one of the things that is probably the biggest value point to Dynamo. I mean, NoSQL databases, there's not a lot of differentiation. You're going to get into, people are going to tell you about this API feature, that API feature. The reality is the design patterns that I implement across all stacks. I don't discriminate against MongoDB, Cassandra, DynamoDB. They're all the same, and the design patterns are all equally applicable. They are all fast and consistent at any scale, but the difference between a DynamoDB and say a Cassandra or MongoDB is really about scale. How many people in the audience have managed NoSQL databases at scale? I'm talking like 50 plus nodes, right? So not very many. When you get into, there's a few. The amount of overhead that goes into managing that system when you start to scale out the cluster is extreme, right? I have customers that have 724 NOCs staffed 365 days a year with engineers that their only job is to keep the Cassandra cluster online, right? Or keep their MongoDB shards running. I've had customers with, trying to add new shards into their clusters, and they're under pressure, under high utilization, and they can't even get the clusters to replicate and bring the new capacity online without API throttling their services to reduce and eliminate the back-end processing pressure on their clusters. And so managing that infrastructure at scale becomes an extreme investment for an organization, a very large investment that most companies don't want to make at some point. So most of the customers I talk to are the guys that have scaled out to the point where they realize that's just not a cost that they want to maintain. Now, how do I get this thing into a fully managed service like a DynamoDB? When you look at DynamoDB schema, like all NoSQL databases, we have some form of a table or a collection or a key space. That's really what a table is in DynamoDB. They call it a key space in Cassandra. They call it a collection in MongoDB. It's all the same. Items exist inside of a table in DynamoDB. Items have attributes. They don't all have to have the same attributes. That's kind of a fundamental characteristic of all NoSQL databases. Is they say schemaless. I say not really schemaless. I say flexible schema. But it allows us to put multiple types of objects onto the table, right? Not just one type of object. In DynamoDB, we provide a partition key, which is mandatory. It uniquely identifies the item. We have an optional sort key that you can provide. If you provide the sort key, then it's the combination of the partition key and the sort key that uniquely identify the item. What this really means is now the partition key identifies a folder or a bucket, and the sort key identifies the order of the items within that folder or bucket. And I can execute complex range queries against the sort key attribute to be able to filter and create selective result sets. So if you think maybe the partition key might be a customer ID and the sort key might be the order date for a given customer, and my primary access pattern might be get me all of the orders for a given customer in the last 24 hours. I could say select star from table where customer ID equals X, sort key is greater than 24 hours ago, and I could have 2 years worth of orders for that given customer, but I'm only going to get the orders that match that particular sort key condition that I provided. So there's all kinds of range operators available for you to be able to filter and select those result sets out of those individual partitions. But this is the fundamental construct that we're going to maintain in DynamoDB, is that kind of partition and sort key relationship to be able to group and aggregate the items on the table. Again, all NoSQL databases use similar constructs. In MongoDB, you could call this the shard key and an index versus a partition key and a sort key, but the same constructs apply. So SQL versus NoSQL. Typically, in the past, this is how we maintain those relational data in a relational database. And this is an example of a product catalog. We have all of the common relationships that we would expect to see in a relational database. A one-to-one relationship between products and books, albums and videos, one-to-many between albums and tracks. We have a many-to-many between videos and actors, because actors can be in many videos. So if you think about the types of queries that we'd have to execute to get a list of my products, right, it's 3 individual queries joining up to 4 tables of varying levels of complexity, and this gives you a good idea of why NoSQL or relational databases have trouble scaling, because that CPU is hopping all over that disk trying to assemble this denormalized view that the application is actually requiring when I say, hey, give me all of my videos, right? And give me, and I want all, everything, the whole actors in the video and the whole 9 yards, right? It's going to denormalize that into a view and serve it up to the user. And this is really, if you get into why was relational database invented? It was invented in the 60s and 70s, late 60s, early 70s, because storage was extremely expensive. So a story I like to tell is when I was in the mid-'80s, I was at Macworld in Moscone Center, and I was walking through the convention center, and I saw a truck transmission in the middle of the conference center. I said, why is there a truck transmission in the middle of Moscone Center? And I went over there and looked a little closer, and it wasn't a truck transmission. It was a hard drive from 1974, and it was cross-section. It was really cool looking because all those platters and everything all cut in half. But it had a little sticker on it that said, capacity 4 megabytes. I was like, wow, that's a pretty big disk for 4 megabytes. And then underneath it said MSRP $256,000. I went, whoa. So back in 1974, I guess we weren't storing a lot of data on magnetic disk. Probably not. But the point is, yeah, we were probably using paper tape, magnetic tape, and all this kind of stuff, floppy disks even. But the reality is storage was extremely expensive, and the sprawl of data on disk was causing data centers to rack nothing but more and more and more storage arrays, right? So we wanted to decrease the pressure on the storage subsystem, so we developed a relational database which does a beautiful job of normalizing the data, deduplicating that data on disk. Gives me an ad hoc query engine so I can restructure that data on the way out, but it comes at a cost, and that cost is CPU, right? But we didn't care about that in 1970. We cared about the storage. Now fast forward 40 years, and that is not the case today. Today I pay for CPU seconds. I pay pennies per gigabyte for storage, so why would I use a relational technology that's optimizing the least expensive resource in the data center? And that's really what we're doing when we start looking at NoSQL. So there's a reason, there's a method to the madness here. We're not just changing things because we like to. We're changing things because we have to, because it's not cost effective to use a relational database for big data applications. And one of the things I'm seeing, the huge trend I'm seeing in the industry is, if you asked me a year ago even, where I thought the NoSQL technology, I mean, I would tell you right away that it was, well, I think there's this class of application, but it's not the common class, it's the big data app. Today, I'm seeing that the common app is starting to become the big data app. More and more, I'm working with customers and I'm looking at applications that just a year ago weren't working under the same data load that they are today. And it reminds me of the early days when we would talk about sizing a workload and estimating, and we're always wrong, right? If something's successful, it always ends up consuming a lot more than we expect. And that's what I'm starting to see in this trend. So maybe a better approach to this is to use a denormalized data structure where I'm going to take those hierarchical items in those tables and I'm going to rotate all of those rows into a hierarchical data structure, a document, or a collection of items that live in a single partition on my table. And now, if I want to get all the products on the table, I have a very simple query: select star from products. Wow, I've eliminated all the complexity and multiple round trips to the database and a lot of CPU load simply by denormalizing the data and storing it in a little bit different way. So this is kind of the general approach we're going to see with NoSQL, right? We want to denormalize that data so that we can distribute the processing and make things scale a little bit easier. When you get into graph databases, we have a great offering, Amazon Neptune, and really graph databases are about relationships. It's about querying those relationships. Relationships in a graph database are first-class entities. What does that mean? It means they have properties. Right? In a relational database, I have a one-to-many relationship, but those relationships don't have properties in and of themselves that define how are these items actually related to each other. If I want to do that in a relational database, I have to create this little lookup table, and then the lookup table can have properties on the mapping between the parent and the child and whatnot, but it becomes, again, another step, another aggregation function that the CPU has to execute in order to be able to provide that data. So Amazon Neptune is out there for you. It's a fully scalable graph database, supports millions of transactions per second across multiple read nodes. Very, very powerful system. And if we get into what kind of workloads make sense for graph, then there's a very specific class of workloads that work very well with the graph database, and typically it involves traversing those relationships. So, if you find yourself querying a database and round tripping back and forth multiple times to get the answer that you want, then maybe it's a good workflow for graph. So let's talk about a recommendation engine here where I have, maybe a user's going to visit Paris. He's interested in the Mona Lisa. He wants to see other things in Paris that his friends, have seen and liked. And so if we look at the approaches that we can take to solve this problem, maybe the first approach is to use a normalized graph design. This would be a relational database, purely relational, fully normalized. And you can start to think about, okay, well, if Bob wants to find out all of his friends, first I have to query for all of Bob's friends, then I have to query for all the things that Bob's friends have done and liked, and then I have to go and so I'm making multiple round trips through the database to be able to get the lists of data that I need to process in order to determine what are the things Bob might want to see when he goes to Paris. Obviously not a very efficient approach. I'm going to have to round trip back and forth this database multiple times to get all of the various items and whatnot that are related in order to be able to come up with an answer. And a different approach might be to say, let's denormalize that graph into an adjacency list, right? We've been solving graph problems for a long time without graph databases, and this is how we've done it. You build these denormalized views where I create a table, and on this table I have nodes, and each one of the nodes has relationships defined within these nodes that define how they're connected to the other nodes of the graph. Right? So in this case, let's say we want to get all the edges that are connected to Bob. Right, that Bob is connected to. I can select star from the table where the node ID or the partition key equals Bob. And I'm going to get all of the things that define Bob and his relationships to all the things that he's chosen to relate to. If I want to get all the types of edges or all of the edges that have chosen to connect to Bob, then I could create inverted indexes on the type of relationship between those nodes. I could index the endpoints of the relationships between those nodes, and I can query one side or the other of that many-to-many relationship. But we're still stuck in that same problem if I need to actually traverse the edges. In this use case, Bob wants to see the Mona Lisa. While he's in Paris, he wants to see other things. Okay, now I have to round trip multiple times through to get all the things that Bob's connected to, all the friends that have visited Paris, all the things that they've done in Paris. I'm traversing the relationships. Okay, I'm making multiple round trips to the database. It's inefficient, high latency process. So this is a perfect example of what a graph database gives you, is the ability to query those edges behind the API. I can make one query of a graph database. So if you look at the graph query types, we have a node query is kind of the primary query, and this is like what entities are in the graph. I can do this with a relational database or a NoSQL database or a graph database just as easily. I have an edge query that gives me, what relationships do the graph entities have to each other. I can do this again with a relational database or a NoSQL database or a graph database, but that last one, that hybrid query, the traversal, this is where graph databases shine, because now I don't have to traverse the edges. I can query and say, give me everything that is related to Bob, all of his friends, and what they've done and the things they like, and I'm going to be able to make one query of a graph database and retrieve all of that data in one round trip. So that's a primary advantage of that graph database, is when I actually need to traverse the relationships between the entities in my application. That's when I'd actually pull that out. All right, let's move on to get into Redshift. Redshift is about data warehousing, fully scalable backend. One of the most powerful features of Redshift is elasticity, right? We can resize the cluster up and down as the performance and capacity needs change, which is not something you can do with an on-prem data warehouse, right? An on-prem data warehouse is provisioned at 100%. It sits there, spinning disks and spinning CPU, whether I'm using it or not. With Redshift, I can actually spin up the capacity I need when I need to execute those decision support system style workloads or those data warehousing workloads, and spin it down when I don't. Save yourself a lot of money that way. Athena is another way to be able to manage DSS style workloads against a data lake. If I have semi-structured data in S3, a really nice thing about Athena is it's serverless, completely serverless infrastructure for doing these types of analytics. You pay only for the queries that are run, and it's very open and easy. One of the nice things about it is JDBC, ODBC connectors. You can build your application, connect right to the Athena service, and again, you pay only for the queries that you run. Just point the thing to S3 and execute those complex SQL queries against the data that you have archived. And I believe the Glacier feature is still in a coming soon state. I noticed this before the session. It says, I should have checked that. It might actually have been released by now. But we will be able to query the data that you actually have stored in Amazon Glacier as well with the Athena engine. QLDB announced earlier today. This is a fully managed ledger database. This is really cool, really exciting, because this gives us a system that gives us, it's a append-only immutable journal, right? So one of the things that we run into oftentimes is the ability to guarantee an audit trail. How do I guarantee an audit trail in the system, right? I cannot stop a malicious actor from coming in and changing the data underneath the covers. No matter how much code I write at the application layer, if somebody comes in directly to the database and starts executing queries against the data in the database, then that data could be changed without the application layer being aware of it. With a ledger database, that is not the case, right? It's a mutable and transparent a journal that's cryptographically verifiable. Is probably the most powerful feature of a ledger database. So when you have those use cases that have that kind of compliance requirements around auditing, audit trails, whatnot, this is a really good solution for you. The other thing we have just recently announced is a time stream, which is time series database. This was A really neat system to be able to process that and analyze data that is optimized for time series. So anyone who's using familiar with IoT type of applications, oftentimes that's exactly what we're doing. We're managing that time series data. We're in bucketed partitions where we need partitioned metrics. Amazon's time stream is optimized for those workloads. So again, purpose-built database solutions for just about every single type of workload. When you get into what to use when, it's really about again, these dimensions. If I'm looking at an SQL database, then I'm looking at normalized relational data or dimensional, maybe snowflakes type schemas. I'm going to load into a Redshift or data warehouse. I'm running ad hoc queries and aggregations. I'm going to scale vertically. Right? I got to scale within a single system, a single box, and it's really good for those OLAP or DSS style workloads, right? Decision support system workloads. Analytics, access patterns that are not well understood. These are really good use cases for SQL. No SQL is really optimized for compute, right? So again, SQL optimized for storage, no SQL optimized for compute. I'm going to spend more time up front modeling my data with a no SQL database. I'm going to need to understand the access patterns of that particular application. They're going to need to be definable, well understood. Once I've done that, I'm going to spend the time to denormalize that data, and then I can store it as, I guess you could say, a collection of instantiated views or pre-computed aggregations that I can call up with simple queries. I'm not going to ask the system to compute a lot of data on the way out. I want that read pattern to be highly efficient. So, and when we denormalize the data model, now we can scale horizontally across multiple boxes. Again, for nearly unbounded throughput and capacity. No SQL databases are absolutely fantastic. And then the last category we have here is that graph database. And the graph database is about relationships. Right? Denormalized entity relationships, traversing the graph, so to speak. It's really, really good for ad hoc queries against those relationships. One of the nice things about a NoSQL database, we showed that adjacency list model, I can actually pre-compute the graph aggregations and write those into the edges. And if you think about common social networking applications like Facebook or LinkedIn, things like this, those are not running on graph databases that are computing the results ad hoc every time I want to get the list of friends of my friends, right? Or the connections, my second and third level connections. Typically what happens in those applications is they're going to have a batch process that runs on a regular schedule. It's going to modify the data that's related to my user to include those graph projections so that when I make the query, I don't have to actually compute the result. It's reading the result to offload the CPU. So it'll be eventually a consistent view, but it's going to be a much more efficient view. So it depends on the nature of the workload, right? If I want to support those ad hoc entity relationship aggregations, then graph databases are wonderful solutions. And so it's kind of a hybrid scale model, and it's designed for those graph traversals. So when we get down to it, there's a couple of dimensions to your workload. I like to call this the iron triangle of purpose, or the pie theorem, because I like pie. It's tasty. But the bottom line is you have a couple of dimensions. The first dimension is pattern flexibility. This is the ad hoc queries. Do I understand my access patterns? Are they well understood or not? If they're not, then I need that pattern flexibility. That's one of the dimensions of the iron triangle of purpose. If I have the need to scale for all practical purposes without bound, right? That infinite scale, if I have the need for that, then that's another dimension, right? How much scale does my application or does my workload require? And then there's efficiency. How fast does the result need to come back? And these are the three fundamental dimensions of any given workload. And if you look at Amazon's solutions that are available, we have solutions available for every single category. If you look at the PI solution or pattern flexibility infinite scale, that's a data warehousing workload. I don't care about the efficiency. What I need scale, and I need the ability to answer ad hoc queries and questions that I don't necessarily know what they are right now. And that's a data warehousing or a decision support system that works very well with Amazon's Redshift or Athena offerings. If you look at the IE or the infinite scale and the efficiency dimensions, then we're really talking about a denormalized data store with well understood access patterns because I don't need the pattern flexibility. This is an OLTP application, and this is going to be a beautiful application for Amazon's DynamoDB. And then the last category would be the PE dimension, or pattern flexibility and efficiency, and this is where we're getting into ad hoc queries. And I need to have low latency response times. So maybe OLTP applications that don't require a lot of scale could be supported by these systems, or I need OLAP style applications or operational analytics where I'm trying to answer questions in real time of my data. And I don't know what questions are going to be answered or asked. Multi-dimensional searches, users have the ability to come in and say search on n number of dimensions. These are the types of applications that run much more efficiently with a relational database. I put Neptune in this category as well because it excels at ad hoc graph queries, even though it's a NoSQL database, that its sweet spot is in those ad hoc graph aggregations. So there's a really good dimensional graph here that you can look at and say, okay, what is my workload? Do I need pattern flexibility and infinite scale? Do I need infinite scale and efficiency? Do I need pattern flexibility and efficiency? And we kind of break things down into one of those three categories, and we can really pick the database that's going to be the most effective for your solution based on those dimensions. When you get into DynamoDB as a service, the reliability of the service is undeniable. I mean, it's what we call a tier 0 service at AWS. It backs other AWS services. As a matter of fact, in our region build process, a region cannot even go live. Other services are built on top of it. So when we actually lay down the foundation of a region, DynamoDB is one of the very first services to come online, if not the first. Hundreds of thousands of customers use DynamoDB for just about any given workload that you can think of. Some of the most mission-critical workloads in the world. How many folks in the audience have a Samsung Galaxy phone? All right, you're using DynamoDB because the Galaxy Sync service runs on top of DynamoDB. As a matter of fact, almost every one of you guys, if you pull out your phones and start flipping through your apps, I could point to a dozen applications that are probably installed on your phone that are actually using DynamoDB. That's how distributed or how ubiquitous this technology is. You don't even know that you're customers, but you all are customers. Hundreds of thousands more use RDS. Obviously, RDS is a technology, relational database technology has been around for 40 years. It's not going away anytime soon. Oftentimes, the easiest way to get your applications into the cloud is to lift and shift, so to speak. Maybe you're not experiencing the scale pressure that makes it necessary to migrate that application to DynamoDB, but you're not interested in managing that infrastructure anymore. That's one of the best things about RDS is it's fully managed. You don't have to worry about patching your servers or rebuilding your volumes. If you get storage corruption, that's our job. So let us do that heavy lifting. If you look at purpose-built database solutions, it's all about offloading that infrastructure management from you. I mean, think of all the things that you can do if you didn't have to worry about capacity planning, provisioning, monitoring, OS patching, hardware upgrades, provisioning for new regions, and not only that, software, database upgrades, security patches, scaling that system, monitoring, performance tuning. These are all things that are not core to your business. So don't do it. Let us do it. Let the managed service providers do it. We actually are really, really good at this stuff because we've been doing it for a long, long time. And not only that, but can you do this with zero unplanned downtime, or in the case of like a DynamoDB, zero downtime? As a matter of fact, I don't even say zero. We have an SLA up on DynamoDB. It's 4.9 SLA in a single region. If you go global tables, it's 5 nines. If anyone has tried to maintain IT infrastructure with a 5.9 availability, you'll know that's like seconds of downtime per year. All right? That's not easy to accomplish. We do it every day. As a matter of fact, we have to do it every day because, again, Amazon DynamoDB is a tier 0 service with other AWS services built on top of it. If we go down, regions go down. We've never seen a region failure. So that's a testament to the reliability of DynamoDB. All right, that's what I have for you guys today. Thank you so much. I'll be taking questions out in the hallway out there.